Our next speaker is Kathleen Morse from her company Advanced Materials Applications, and she'll talk about her work on the ISS for radiation testing.
Hello, so I'm the founder of Advanced Materials Applications, and I'm also the CASES-sponsored principal investigator for the project of evaluating gumsticks computer-on-module technology for use in low Earth orbit. My team consists of a software engineer, Jeremy Zawadny. My radiation effects expert is John Sampson at Honeywell, and we're working with AstroDev to integrate the payload. So there really is a need for terrestrial computing power in space. If you look on the left here, you can see the Proton 200K. It is a space-qualified digital signal processing board. It's about 10 centimeters by 16 centimeters. It costs about $120,000 for one unit. If you look below that, you see the gumsticks computer-on-module technology. It contains the digital signal processing board in addition to graphics processing and also general purpose processor. It's about the size of a gumstick, 6 by 2 centimeters, and it costs about $100 to $200. So to summarize, space-qualified computers tend to be a few generations behind the state-of-the-art terrestrial processing technologies. They tend to be about 2,000 to 5,000 times more expensive, and they also are significantly larger in size, weight, and power consumption. There really, again, is a need for space-based computing power to support computationally demanding tasks, such as signal processing and analysis, data capture, and sensing and detection. There are several benefits to using gumsticks in space. As I've mentioned, they're a small form factor. They have a power consumption at a full task load running of about 2 watts, and they're also only weigh grams. They use current generation OMAP processors with ARM Cortex-A8 architecture. They've been proven in many terrestrial-based applications, including mini supercomputers. Sandia National Labs had about a medium-sized suitcase filled with 200 nodes to make up a 200-node mini supercomputer. They've also been proven and used in robotics and unmanned air vehicles. They're currently being studied for use in the dependable multiprocessor by Honeywell. And if you see the picture in the upper left there, she's holding an aluminum chassis that contains 8 gumsticks modules, so that's 8 computers in her hand. So this is really the first will-be-published study of gumsticks used in low Earth orbit. And this is a really important step towards their use and integration into, fault-tolerant computers for critical or non-critical type space missions. So basically, the gumsticks will be on the outside of the ISS. You see a blow-up at the bottom of the external module that'll be attached. And there's some key questions we want to answer. We want to know how the low Earth orbit space environment will affect the gumsticks modules. The low Earth orbit space environment contains high-energy protons and heavy ions, and these are known to cause single-event effects, so we want to understand what's going to happen to these. In addition, what is the net operation time or uptime for each gumsticks module? Basically, each of these modules will be connected to a watchdog, and when there's a detection of a high current latch-up or a single-event functional interrupt in which the heartbeat to the processor is lost, the watchdog will then reset power to the module and record the event. But basically, if the module doesn't operate a majority of the time or even a significant fraction of the time in space, then these won't be very useful for space applications. In addition, is the gumstick module performance affected by feature size? 3 of the modules we're flying will have 65 nanometer CMOS technology, and 1 of them will have 45 nanometer CMOS technology. Smaller feature sizes tend to have more single event effects, so we're going to be looking for that kind of trend. Using codes like SPENVIS, we simulated what the low Earth orbit space environment will look like with a 6-month exposure to space. On the left, here you see the total ionizing dose plot as a function of chassis thickness. And basically our total ionizing dose exposure will be significantly less than 0.1 kilorads, so we're really not going to see any total ionizing dose degradation. In addition, we mapped out the integral proton flux, and as you see in this plot, you've got the flux of protons as a function of the energy of the proton in MeV. And you see that they will be exposed to up to 200 MeV protons. So we'll be looking basically at radiation effects both on the ground and in space. So the space payload is, as I show you there, it's going to be in the external rack. That red dot there is pointing in the anti-velocity vector for the International Space Station. And that's actually where the 4 gumsticks modules are going to be located. So they'll basically get a non-shielded exposure to space. We're through CASIS, we're working with nanoracks to develop the chassis, which will hold the 28 volts and the 30 watts of power, and basically help us to connect basically all the data coming from our payload to their downlink system on the ISS. So on the top here, you see the gumsticks board, and then next to that, on the side here, that'll be holding all the watchdog electronics, and that will contain rad hard and rad tolerant technology. So for the space flight experiment, which will be 6 months exposure to the outside of the ISS, we'll be flying 4 different models of gumsticks. These include the Sandstorm, which has the 45 nanometer CMOS technology, the Earth, the Water, and the Fire. During flight testing, we'll be looking at the CPU performance and also the performance of the RAM and the NAND flash. And as mentioned, the data from this will be downlinked to Earth in semi-real time. In addition, before and after the experiments, we do kind of a high-level functional analysis on the computers, and we'll be evaluating, again, the stability of the general-purpose processor, the rate of errors for RAM, the rate of errors for NAND flash, graphics processor, and also some externals, the Wi-Fi and the Bluetooth. So it's been a really great experience working with CASIS. We've been able to have a fairly quick timeline on everything. I submitted my proposal in December 26th. I was notified of the award, and the program was initiated in April. And then since then, I did 1 proton test at 64 MeV and plan to do 2 more proton tests. And we have scheduled delivery to nanoracks for payload integration. This will be the 1st of March. And then there will be the launch and delivery to the International Space Station of September. And then we'll have that 6-month space exposure, and then it'll be returned back to Earth in early 2015. Okay, thank you.
So questions for Kathleen?
Yeah.
So, Rick Vaughn, computer scientist. So when you did the proton test, I mean, were you on the ground? Were you expecting anything to fail? Did you live up to your expectations, or what happened?
Well, we expected to see single event functional interrupts, single event upsets, and latch-ups, and we did see all 3. I'm waiting to do a little bit more proton testing before I comment much more on the results, but it pretty much behaved the way we expected. Any more questions? Yes.
Eric Brock, I was assuming that everything were to work out and prove that the gumsticks were very robust in space. What is do you see as going forward? It's like the business model to scale this up beyond an experimental level.
Well, so basically, gumsticks is one system-on-a-chip type technology. We're interested in looking at others. But yeah, so first you want to do testing to basically then down-select the most robust technology. And then what you could do is basically, pick the best technology and then develop custom boards for space applications. The business case is pretty strong. As I mentioned, the price for a space computer right now, their performance is fairly low, and they cost about $2,000 to $5,000 more. So you're already starting with potentially a product that does not cost that much to develop. Obviously, you have to do rigorous testing, and there will be design work because you need to have a fault-tolerant system. The CMOS technology will never be latch-up immune, and so that's a reality. So we have to design for that. So the main thing is you're able to use a product that's much smaller in size, weight, and power, costs significantly less, with a very short turnaround time. And you could potentially use this for non-critical missions such as to the moon and Mars. And there is some interest in this. So, and then for CubeSats, the big application is when you have that much processing power in such a small volume, you can do basically a lot of remote type sensing and detection and remote missions. And again, it makes everything much more affordable when you start from COTS. But it's not an easy problem. I mean, this definitely going to require a lot of rigor and analysis, but we're doing it. And having basically a mission to the ISS paid for is incredibly important.
So one of the attributes of FACES now is risk reduction for you, and probably a much less expensive form of doing that.
Absolutely, yeah. I'm not even sure what it would cost if I didn't have cases, so I don't know if you can comment on that, but.
Are you using the NanoRacks external rack?
Yeah, that's right. Myself and Judd, who's flying the carbon nanotube solar cells, we're the first projects on the outside of the ISS, so we're kind of flying in a prototype. So, yeah.
You mentioned 30 watts. What are you using for heat dissipation?
Basically, we have a heat sink, and the main concern with heat dissipation is the processors not getting too hot. So we will have a thermal sink to the cold sink on board the ISS. That runs between 20 and 30 C. So we're pretty confident about that. But yeah, flying really powerful processors in space, thermal control is another significant issue. Yeah.
Okay, thank you very much, Kathleen. And Kathleen, you were also.